Okay. So, next in that previous topic we have seen that your that three phase fault, but in that case our objective was mainly for Z bus building algorithm and a few numericals we have solved, right. But question is that in the Z bus that we have to have Z bus matrix. So, in any way, so today we will start the other thing, that is your symmetrical component, because symmetrical component is more important for your our fault studies, because most of the fault actually unsymmetrical or unbalanced type of faults, right. Therefore, symmetrical your what you call that symmetrical component will be that your is easy, I mean will be applicable for such kind of fault analysis. So, let us come to your symmetrical component. So, generally in a balanced system analysis can be done on a single phase basis, that we have seen also for three phase fault. The knowledge of voltage and current in one phase is sufficient to determine the voltage and current in other two phases, because it is a balanced system. Real and reactive powers are 3 times the corresponding per phase values. So, for that is for balanced system, but when the system is unbalanced, the voltages, currents and the phase impedances are in general unequal. So, unbalanced operation can result when loads are unbalanced, this is one thing. So, loads are unbalanced means that I mean all the 3 phase loads may be different, and this is more your what you call more applicable to the your distribution low voltage distribution system. For example, in our country say 11 kV distribution system, but or in other parts of this world. So, sometimes what happens that in the 3 phase distribution system loads are not balanced, this is one thing. Second thing, in many places that from the same substation same feeder, right, single phase, 2 phase or 3 phase loads are supplied. So, in that case your things are system become unbalanced. And another aspect is that unbalanced system operation can result, that is due to unsymmetrical fault. For example, that your line to line fault, that is called LLG, right. Then double line to ground fault or single line to ground fault, right. Such an unbalanced operation can be analyzed through symmetrical components, where the unbalanced 3 phase voltages and currents are transformed into 3 sets of balanced voltages and currents called symmetrical components. So, another type of fault happens, but very rare, that is your conductor opening. Suppose one phase conductor your opening means cut, right. So, these are very rare, but question is that that is also called open conductor your fault, but that we will see when we will go for unbalanced or unsymmetrical fault analysis. So, symmetrical components of an your unbalanced 3 phase system, right, this one. So, the unbalanced phasors of a 3 phase system can be resolved into the following 3 component sets of balanced phases, which possess certain symmetry. That means, for unbalanced phasors voltage or current, right, we can resolve into following 3 component sets of balanced phasor, and it has some symmetry. That means, first thing is that a set of your 3 phasors equal in magnitude displaced from each other by 120 degree in phase and having the same phase sequence as the original unbalanced phasors, and this set of balanced phasor is called positive sequence component. So, a set of 3 phasors equal in magnitude, but displaced from each other by 120 degree, the way we have solved the balanced system, right, and as the original unbalanced phasor, this set of balanced phasor is called positive sequence component. Similarly, a set of 3 phasors again equal in magnitude displaced again from each other by 120 degree in phase and having the phase sequence opposite to that of the original phasor. I mean, if for this one, for positive sequence, if it is A B C say, for this one opposite it will be A C B sequence, right, and this set of balanced phasor is called negative sequence component. And last one, that is a set of 3 phasors, they are equal in magnitude with 0 phase displacement. There is no phase displacement between them, but they have equal magnitude from each, and this set is called 0 sequence component. So, the component of this set are all identical. I mean, they all are identical because they have equal magnitude. So, therefore, these 3 sets of balanced phasors are called symmetrical components of the original unbalanced phasor. So, assume that the 3 phasors are represented by A, B, C, and such that phase sequence A, B, C is called positive sequence. So, this is this you know already we have done it, right. So, this the 3 phase system. So, this is A, B, C. So, A, B, C sequence, this is actually positive sequence. Now, say V A, V B, V C are balanced voltages, that is phasors, characterized by equal magnitude and interphase difference of 120 degree. This also you know. Then the set is said to have phase sequence A, B, C or positive sequence, right. That is whatever we have studied little bit for solving, say 3 phase transmission line or this that almost all are ABC, all the ABC your what you call phase sequence. So, if VB lags VA by 120 degree, this you know, and VC lags VB by 120 degree, that also you know, then we can make this kind of your definition. That is that assume your VA is a reference phasor. Suppose if we put like this, say VA is reference phasor. So, VB lags from VA here by 120 degree and VC lags from VA by 240 degree, or otherwise VC leads VA by 120 degree. So, if we define like this, say VA is equal to VA, a reference phasor, VB is equal to beta square VA, I am coming to that, and VC is equal to beta VA, right, where the complex operator beta is defined as, we have taken beta is equal to actually angle 120 degree. So, e to the power j 120 degree. That means, this beta has the following properties: beta square, beta is e to the power j 120 degree, then beta square e to the power j 240 degree is equal to, it is e to the power minus j 120 degree, that is actually is equal to beta conjugate. Similarly, beta square conjugate is equal to beta. If you take beta square this conjugate, that will become beta, and beta cube is 1, because beta cube means e to the power j 360 degree, that is cos 360 plus sin 360. So, it is 1, right, and 1 plus, and this also holds for when beta is equal to the power j 120 degree, then 1 plus beta square is equal to 0. These conditions will be applicable now, right. Now, in this case, that VB is equal to VA angle minus 120 degree here this figure. That means, VB is equal to VA e to the power minus j 120 degree, we can write like that. Therefore, VB is equal to, we can write beta square VA, because beta square is equal to e to the power j 240 degree is equal to e to the power minus j 120 degree. So, we can write VB is equal to beta square VA, that is why we are writing here VB is equal to beta square VA. Similarly, VC is equal to VA angle minus 240 degree, because this VC lags from VA, that is 240 degree. So, VC is equal to VA angle minus 240 degree, that is we have given that your this VC is equal to VA, otherwise VC lags from VA this thing, or VC leading VA by 120 degree. So, same this can be written as VC is equal to VA angle 120 degree, that is VA to the power j 120 degree, that is VC is equal to beta VA. That means, we are writing here VC is equal to beta VA. So, that means this VA, VB, VC, this VB, VC we are putting in terms of a complex operator beta, where beta is equal to e to the power j 120 degree. Next is, if the sequence is ACB, I mean if it is a negative sequence, right, then VA is equal to VA. Now, VB will become beta VA and VC will become beta square VA. Now, sequence is ACB, that means Vc lags from Va by 120 degree, this is your 120 degree and this one also your 120 degree. So, and Vb lags from Va by 240 degree, just whatever we have done previously, it was beta square, now it will beta, it was beta, now it will be beta square. Therefore, Vb is equal to, that is it is lags from Va by angle minus 240 degree, that is actually Va angle 120 degree. So, that is Vb is equal to Va e to the power j 120 degree, that is beta Va. Similarly, this Vc Va angle minus 120 degree lags from Va is equal to Va e to the power minus j 120 degree, that is Vc is equal to beta square Va. So, Vb is equal to beta Va here and Vc is equal to beta square Va, right. Assume now, we will assume now that subscript 1, 2 and 0 refer to positive sequence, negative sequence and 0 sequence respectively. This is actually convention, everyone following this convention. So, if Va, Vc, Va, Vb and Vc represent an unbalanced set of voltage phasor, the three balanced sets are written as. So, that means Va1, Vb1, Vc1, this is positive sequence set, Va2, Vb2, Vc2, that is negative sequence set, and Va0, Vb0, Vc0, that is 0 sequence set. This way we made it. That means we will come later, but that means Va is equal to Va1, Va2 plus Va0, Vb is equal to Vb1, Vb2 plus V0 and Vc is equal to Vc1 plus Vc2 plus Vc0. So, these are that positive, negative and 0 sequence set. A set of balanced positive sequence phase, now same way we will write, the way we have seen ABC sequence here also, this is also balanced positive sequence phasor and sequence is your ABC. So, the way we wrote same we will write, it is we are not writing again Va1 is equal to Va1, it is V1 understandable. Vb1 will be beta square, just 1 minute, the same thing, Vb will be is equal to your, we have made it no, Vb is equal to beta square Va1 and Vc is equal to beta Va, that is for ABC sequence. This is also we are making it Va1, Vb1, Vc1. So, here also Vb1 will be beta square Va1 and Vc1 will be beta Va1. Here it is ABC sequence, here is the positive sequence, negative sequence and 0 this thing, your 0 sequence component, same thing will come. So, for positive sequence, that Va1 for phase A to this one, for phase B positive sequence Vb1 will be beta square Va1, for phase C positive sequence Vc1 will be beta Va1, same your equations, only you have to represent Va1, Vb1, Vc1, same philosophy. Similarly, the same thing, same way will follow when ACB sequence, that is a set of balanced negative sequence phasor, it is Va2, it will be Vb2 is equal to beta Va2 and it will be Vc2 is equal to beta square Va2. This is equation 3. Now, a set of 0 sequence phasor, they all are same. So, it will be Va0, Vb0 will be Va0 and Vc0 will be Va0. This is equation 2, 3 and 4. Now, this set, these three phasors Va, Vb, Vc can be expressed as the sum of positive, negative and 0 sequence phasor defined above. That means, Va is equal to Va1 plus Va2 plus your Va0. So, here we can write Va is equal to Va1 plus Va2 plus Va0, this is equation 5. Vb is equal to Vb1 plus Vb2 plus Vb0, equation 6 and Vc is equal to Vc1 plus Vc2 plus Vc0, that is equation 7. Now, this is your positive, negative and 0 sequence your component. Here I have made this is Va1. So, Vb1 is equal to beta square Va1 and Vc1 is equal to beta Va1, this is negative sequence. Va2 and this is reference one, Vc2 is equal to beta square Va2 and your Vb2 is equal to beta Va2 and this is your 0 sequence, this is positive, negative, this is 0 sequence, they are all in same phase, right. So, it is Va0, it is Vb0 is equal to Va0, Vc0 is equal to Va0 because they have equal magnitude. So, these symmetrical components of your unbalanced voltage phasor. So, easily you can make this one. Now, let us your express equation 5, 6 and 7 in terms of the reference phasor VA1, your VA2 and VA0. Therefore, current will come, that current also same philosophy, that VA is equal to VA1 plus VA2 plus VA0. So, VB is equal to your beta square VA1 plus beta VA2 plus your VA0. Actually, VB is equal to, just hold on, let me show you that thing. So, this equation, it is VB1 plus VB2 plus VB0. So, VB1 is equal to your beta square VA1 and VC1 is equal to beta VA1. So, in this equation it is VB is equal to your, in this equation VB1 you substitute beta square VA1, VB2 you substitute beta VA2 and VB0 is equal to VA0, your VB0 is equal to VC0 is equal to VA0. So, VB0 is equal to VA0. So, this is VB. Similarly, your VC is equal to VC1 plus VC2 plus VC0, and your same way, right, you can make your this VC1 is equal to beta VA1 and VC2 is equal to beta square VA2. Same way you put here, that the way we have made it, that your VB1 beta square VA1, your VB2 is equal to beta VA2, same way you put it here, VC1, VC2 and VC0 is equal to VA0. I mean, this will come beta VA1 plus beta square VA2 plus VA0. That means, this VA, VB, VC all actually represented by VA1, VA2, VA0 and the complex operator, that is beta. So, this is equation 8, 9 and 10. Now, this equation you put them in matrix form. So, it will be VA, VB, VC and it will be 1, 1, 1, beta square beta 1, beta beta square 1 and VA1, VA2, VA0. So, these three equations you put it in matrix form. Next is this equation only we can write that Vp is equal to AVS. This way we write, where Vp is equal to VA, VB, VC transpose, right, and Vs is equal to VA1, VA2, VA0 transpose, and A is equal to that matrix 1, 1, 1, beta square beta 1 and beta beta square 1. This is equation 13. So, this equation 12, this equation can be written as Vs is equal to, this Vs is equal to A inverse Vp. This is equation 14. So, the A inverse, if you take the inverse of this matrix, it will be A inverse will become 1/3 1 beta beta square 1 beta square beta 1 1 1, but you need not take directly that inverse. I will show you one methodology, that how one can remember, right. Basically, A inverse is equal to 1/3 A conjugate transpose. I will come to that. So, if you take the complex conjugate of this matrix, right, that is your A matrix, you take the complex conjugate of this matrix, that is equation 13, then A conjugate will be, this is 1 1 1, it will beta square conjugate, it is beta conjugate, it is 1, beta conjugate beta square conjugate 1. Earlier in the beginning I have given, this is 1 1 1, that beta square conjugate is equal to beta, at the beginning this has been given, beta conjugate is equal to beta square, that also given, and 1, same is here, beta conjugate is equal to beta square and beta square conjugate is equal to beta, and this is 1. So, first you take the A conjugate. After this, this is actually A inverse, if you take to that. After this, you take the transpose of this matrix, that is A conjugate transpose, you take the transpose of this matrix. If you take the transpose of this one, so A conjugate transpose is equal to 1 beta beta square, 1 beta square beta and 1 1 1. So, using equation 15 and 16, so this is your A inverse. If you try to find out A inverse of your own, it will become like that. This is actually A inverse. So, that means A inverse actually 1/3 A conjugate transpose. That means, if you know the A matrix, you take the A conjugate, then you take the transpose and divide it by 3, that is A inverse 1/3 your A conjugate transpose. This is equation 17. So, this is easy to remember. If you know that your what you call that A matrix. So, and A inverse will be 1/3 A conjugate transpose. So, it is easy to remember. So, using equation 14 and 15, right, we get. So, equation 14. So, let me go back to equation 14. So, this is equation 14, that V s is equal to A inverse V p, and that means if you that means V p is equal to your V a V b V c, and V s is equal to V a 1 V a 2 V a 0. That means positive sequence component, that V a 1 you can write 1/3, because 1/3 is here, right, there it is in that, right, because it is A inverse. So, 1/3 is there. So, V a 1 is equal to 1/3 V a plus beta V b plus beta square V c, this is equation 18, and V a 2 is equal to 1/3 V a plus beta square V b plus beta V c, this is equation 19, and V a 0 is equal to 1/3, in bracket it is V a plus V b plus V c, this is 20. So, similar philosophy is applied to current, same thing, same positive negative zero sequence component, right. So, in this case the symmetrical component transformation given above for voltages can also be applied automatically for a set of current, same philosophy. Therefore, I a is equal to I a 1 plus I a 2 plus I a 0, this is equation 21. I b is equal to same as voltages, beta square I a 1 plus beta I a 2 plus I a 0, and I c is equal to beta I a 1 plus beta square I a 2 plus I a 0. So, this is equation 23, same as voltage, you will get I a 1, that positive, negative and zero sequence component of say phase A. I a 1 is equal to 1/3 I a plus beta I b plus beta square I c, this is equation 24. I a 2 is 1/3 in bracket I a plus beta square I b plus beta I c, say it is 25, and I a 0 is 1/3 I a plus I b plus I c, this is equation 26. So, voltage and current same philosophy. Next is your power invariance. So, we have to show that is the power equation also original thing and transformation both are matching. So, the complex power in a 3-phase system is given by, we have already seen it before, that S in general it is your what you call V transpose your I conjugate. So, we can write S is equal to V p transpose I p conjugate, that is V p transpose is V a V b V c, that we have given, and I p transpose actually I a conjugate, I p actually I a I b I c. So, it is conjugate. So, I a conjugate, I b conjugate, I c conjugate, multiply, you will get S is equal to V a I a conjugate plus V b I b conjugate plus V c I c conjugate, this is equation 27. Also, S is equal to your V p transpose I p conjugate, this one we have seen before, that V p is equal to A V s, that we have defined. Let me show you once again, that V p is equal to A V s, that is equation 12. So, put here V p is equal to A V s. Similarly, your same philosophy I p also will become A I s, same philosophy. This is directly I have written, but philosophy remains same for voltage and currents. So, it will be A V s transpose then A I s conjugate. So, A V s transpose means this one, V s transpose then A transpose then A I s conjugate, that means A conjugate I s conjugate. This is actually equation 28, but A I s I have not shown that, but understandable both are same, voltage and current philosophy remains same. Now, if you make it, A matrix is known to you, right, A, that means this is your A transpose A conjugate. If you multiply A transpose A conjugate, it will be 3 into an identity matrix, that is 1 0 0 0 1 0 0 0 1. So, A transpose, if you do so, it will be 3 into an identity matrix. That means, S is equal to actually 3 V s transpose I s transpose. That means, A transpose A conjugate is an identity matrix, right, multiplied by 3 of course, that means it will become 3 V s transpose I s conjugate. That is why we are writing that it is 3 V s transpose I s conjugate. So, directly we are multiplying, not writing this, that V S transpose is V A 1, V A 2, V A 0 and I S transpose is I A 1, I A 2, I S 0. So, if you multiply, it will be 3 V A 1 I A 1 conjugate plus 3 V A 2 I A 2 conjugate plus 3 V A 0 I A 0 conjugate, sum of symmetrical component power. So, that means S is equal to whatever you get here, equation 27, that is actually equation 29, they are same, I mean they have to be same, right. So, now sequence impedance of transmission lines. So, that is, now we have to go for sequence impedance of each component, particularly the transmission line, transformers, then synchronous machine. So, just see how we will make it. So, sequence impedances of transmission lines. So, transmission line actually is a static device and hence the phase sequence has no effect on the impedance, because currents and voltage encounter the same geometry of the line. So, for the transmission line, that it basically again I am saying there is a static device and hence the phase sequence has no effect on the impedance, because currents and voltage encounter the same geometry of the line. Therefore, positive and negative sequence impedance of transmission lines are equal, that is Z 1 is equal to Z 2, these two are equal for transmission line. But as means we have discussed before that zero sequence current are in phase, V A 0 your I A 0 same as voltage, I A 0, I B 0, I C 0, they are in phase and flow through the phases, that is A, B, C conductors, and to return through the grounded neutral. So, the ground or any shielding wire are in the path of zero sequence and zero sequence impedance Z 0, right. So, that means for the transmission line, ground or any shielding wire, right, are in the path of zero sequence and zero sequence impedance, that is Z 0, which includes the effect of the return path through the ground, that is different from Z 1 and Z 2. So, the zero sequence impedance for transmission line is different. So, to get an idea of your Z 0, the zero sequence impedance of the transmission line, right, you will consider only 1 meter length of a 3 phase line as shown in figure 2, I mean this figure, right. So, this ground surface actually is approximated as an equivalent fictitious conductor located an average distance, right, from your what you call from each of the 3 phase. Actually, this DN I have shown it very close, I should have shown a little bit away from this, but anyway the ground surface is approximated to an, this is the ground, right, to an equivalent fictitious conductor and located at the average distance dN from each of the 3 phases. So, this is an assumption, So, the phase conductors carry zero sequence current with return path through a grounded neutral. So, for therefore, this is we have take a simple thing, that is equilateral spacing, distance is d, zero sequence current here I A 0, I B 0, I C 0, right, and this zero sequence current your what you call the phase conductors, this is phase conductors carrying the zero sequence current, we return path through a grounded neutral, and this approximation dN actually, that is distance is taken from any phase to the neutral and average distance, this is an approximation only to represent the zero sequence impedance. Thank you, I will come.